but it's all over.
Has everybody read the paper, right?
The net,
ImageNet.
ImageNet,
Yeah.
overfitting.
Overfitting.
There was some about overfitting I heard about that.
Is it though? So, oops. What have we done? This one.
Yeah.
So, what do you think are the main points that like made this paper so successful, or like this approach? Anyone? Yep.
I think at the end of the introduction it said CNNs have fewer connections and parameters, so they're easier to train, but their best performance is only likely to be slightly worse than other approaches.
Let's note that down. So, I guess I don't know how to make this larger, bigger. That's good. Nice. Something like that. So fewer parameters but similar power. Why is that important? Like, why do we need, or why was the fewer parameters important? I mean, the obvious things are, did anybody? Like, I mean, it's pretty obvious. Like, if you
because like the more parameters it has, the more complicated the problem will be. The time it takes for the training time, the runtime will be significant.
Yeah.
Like another thing is like they try to reduce the number of parameter with the same power, and they also use some CPU code to improve the efficiency of CPU. So like, but eventually as a reduction, it still runs for a few days.
Yeah.
The training process. So yeah.
right. Training time, complexity. And memory. Yeah, I think this is like one of the major issues or major ideas here. And so I don't know if you've seen this. This is what I meant with convolutional neural networks are, in a sense, pretty special at that. So if you look at, what was that? Yeah, so our this is like introduction, second to last paragraph, but just the last couple of sentences. Our final network contains 5 convolutional and 3 fully connected layers, and this depth seems to be important. We found that removing any of the convolutional layers resulted in inferior performance. And then the thing that's important, I think, is in the parenthesis, where it's like each of which contains no more than 1% of the model's parameters. So this, like, these convolutional layers are actually like very compact filter networks that can learn something very meaningful and can like represent the data that is presented to them with very few parameters. And just to recap, like, how does that work, right? Like, we talked about this last week. So like, we learn filters instead of like direct network connections, and you apply this filter everywhere on the image. And so the convolutional neural network, so to say, like, each of these filters doesn't apply its function on the entire image, but only on like a very small receptive field on the image itself. And like the further up you go, the larger your receptive field becomes, but you're not working on the pixels anymore, but you're working on these higher representations that are already filtered. So that's very important, I think. Okay, so that is another reason why it's successful. Another reason I would like to add, and we just mentioned that here, is like the depth of the network. So this is something that hasn't like been done there before, and like the important. So when this came out, like this was kind of a new thing to have such a deep network, and that is important because we get more. We get more abstract representations, and if you remember, I think I showed you this before, but these are kind of like these filters that we learn, or that they learned in the network, and so this is what was learned on one GPU, and that was learned on the other GPU. So that was also kind of like revolutionary, that they kind of distributed that across multiple GPUs. So that took a lot more CUDA knowledge than it requires these days to just code in TensorFlow, and like the CUDA connectivity comes for free, so to say. So this is what these representations look like, and the further up you go, the more specific or abstract these filters become. Okay. So what else do you think made this work successful?
They said they use like a ReLU activation instead of like the normal 10.
Yeah.
So a standard wave model neuron was very slow training, but a non-saturated linear was a lot quicker training. What was that about?
So what?
A standard way of modeling the neuron was very slow training, but a non-saturating, non-linear was a quick trainer.
Yeah. So that's what these new or like not very new, but like these neurons, the ReLUs, or the rectified linear units, and we discussed like how their activation function looks like. So they basically have this flat line where it's always zeros, and then like it becomes the input. So basically the way you write this function is just like in like Python or wherever, you just say max of 0 or x. So whenever x is smaller than 0, then you output 0, and whenever you have passed the threshold, you output x. So this is very easy to compute. Also, they have they seem to have like these desirable characteristics where like training seems to converge a lot quicker than with the standard neurons, which doesn't necessarily say that that you can't achieve these performances with standard neurons, but I think it might become a lot more tricky or more complicated to do so. So that was kind of like another interesting way to do that, and make it successful. What other tricks did they use?
Instead of they use like overlapping pooling.
Overlapping what?
Pooling, like the pooling layer.
So pooling layers, they used a couple of them, yes. And I actually skipped that section. So what was special about the overlappings?
They said it was harder to overfit with like it overlapping.
Okay, yeah, I got it. Okay, so so the overlapping pooling is just instead of what the figure looked like when we talked about last week, where the pooling operations, basically if you have outputs from multiple neurons, or like you apply a filter that basically is your filter A here, and it gets input from these, and we can have another one in the middle. So and so on. Obviously, yeah, actually you can have one more here, which is connected to these. So if you do that, and then we said that there is a max pooling, or like any other pooling that you can think of. So if you have a max pool, the non-overlapping pooling works like this. But then you can also have an overlapping pooling where they kind of pool from similar, like, so basically what this S parameter does is that's like a so-called stride parameter, like how much do you move in across the image or across the input, and if your stride is smaller than the receptive field, which is basically written as this Z parameter, then you have an overlap between like several pooling layers or pooling filters. But that, yeah, that's a nice one as well. What else? Another thing that combats the overfitting in their neural network.
They did drop out.
They did drop out, exactly. And for that one, we talked about it. It's basically for that one, it's again like it's pretty. What can I say? It's not really clear how that really theoretically benefits, but it just reduces the availability of too many neurons and too much too much information within the neural network. So it kind of like reduces the network size dynamically with different kinds of regions, or like different kinds of neurons being dropped out, and yeah, it just helps in the training to combat overfitting.
So is data augmentation that part of the same thing?
Data augmentation is another thing, yeah. This is, however, data set specific.
Okay.
And often, I mean, so even though, and this is kind of like what we're going to talk about the next paper, even though you want to learn really from like end to end, where you have raw data input all the way to output, you don't necessarily want to just rely on the raw data all the time. Like sometimes you want to make sure that you don't model too much information, and sometimes you just want to do some data augmentation or some pre-processing on the feature side, even though your network could just take the raw input. What would they do? Looks like they did some PCAs.
So how do they change the intensity of the RGB channel by that?
How do you change
The augmentation, so they say something about changing the intensity of the RGB channel in this one to add multipliers and principal components.
They perform PCA on a set of RGB pixel values.
Or maybe, add multiple principal components. Add.
Yeah, so
That's how you change the channel.
what is interesting here also is each alpha I is drawn only once for all the pixels of a particular training image until that image is used for training again, at which the point is redrawn. So this captures an approximately important property of natural images, namely that object identity is invariant to changes in intensity and color of the illumination. So what that means basically is that they explode their data set, right? So every sample in the training set gets presented with differently every single time. So it's kind of adds a little bit of a noise input to the sample. So that basically creates tiny variations of each image every single time it is presented to the neural network. So that, in a sense, increases the size of the training data set, but also it kind of, again, combats overfitting because it will try to make the neural network invariant for these tiny changes of illumination. And it doesn't, or the illumination and intensity, and they don't, I don't think that they will have, yeah, so the magnitude of these alphas is pretty small. It's it's 0.1 with a standard it's mean zero with a standard deviation of 0.1, so you would expect to draw between minus 0.1 and plus 0.1. A little bit over or under, but it changes the intensities minimally. Okay, it's another good one. Did they do a lot of a lot of work with the learning rate or the update function itself?
What's the stochastic gradient descent learning, momentum update?
So yeah, stochastic gradient descent is a more efficient version of the typical gradient descent or error bug propagation algorithms that we talked about. But there is another detail there. I don't know if you guys have seen that, and we talked about it a little bit, but so this is basically the update function here and the update function. So this here basically is the entire update function, but this is the typical one that we have usually. But then there are two more terms, like this one and that one. So what happens here? So first of all, these are the partial derivatives with respect to Wi. So these are for all our Wi's. That's basically the gradient descent that we're doing. Okay. And then this epsilon here is the learning rate. I don't know exactly what they used here. They'll probably say it somewhere.
What, the weight decay?
No, the epsilon here.
Oh, the epsilon. The learning rate,
I don't know. They might have said it somewhere.
Yeah.
Like I missed it. Anyways, but then there is this other term here, which basically additionally changes every single weight, regardless of what error it does make, right? By another like weight decay measure. So it actually subtracts from every single weight this all the time. Okay, so that means kind of like it suppresses activation in the network, so it makes it more sparse, makes it less active. That's another part that they use. There's another trick that I guess they used. But then there is another term, this one here. Can anybody like interpret what that means?
The momentous dampering parameters?
It's the
0.9?
it's the momentum term, yes.
Yes, dampering.
So
What?
uh,
Momentous updates.
let's add this like so weight decay. And then momentum term. So what does this do? So let's inspect this. So this is the update where the weights at time I plus 1 are defined as the weights at time I plus this eta or v or whatever nu or v I plus 1. So this is this one here. So this is how we update our weights for the next step. This is kind of like our delta, right? And then, so this is at time plus 1. But then this is the same variable, but at time I. So what does that part do to the update function?
This should be like the learning parameter.
So it like gets less and less over time.
The dampering parameter?
So the new one is this part here
Okay.
plus
The decay weights.
this thing, which is 0.9 times the old one. So that kind of, what that does is it stabilizes the direction of like where you update your weights in. So you keep 90% of what you did the last time in your memory, so to say, and you will do that same treatment 90% or 0.9 times to the next time step. So that basically, and then obviously in this one here, you have also the previous step, but then factored in as 0.9 square now. And then the previous step, 0.9 cube, and then on and so on, right? So you kind of reduce what you did in the past, over, like a little bit, but it still factors in, so to say. So that smoothes out what you're doing, like how you're updating the weights. Okay, so that's called a momentum term. It does also, it can be used in other ways as well. We talked about it a little bit, where you can have these arrow functions where you have these plateaus, right? And if you're up here, the momentum term can basically help you speed up across these plateaus, because you're like adding what you did previously into it. So sometimes if this sometimes you have like additional functions, but they don't have the luxury to do this because it's such a like big network and they have to update so many things. But sometimes you would have also like a check if the sign of this one or of this part here changed from one step to the other. So like if you sped up too fast across this part here and you realize, oh, like my gradient changed that direction. So like if you have something like this, where you jump over here from here where the gradient goes in that direction or the negative gradient goes in that direction, while you realize here it goes in that direction. So now you have to realize that, oh, I jumped over a valley, right? So I need to go back and then reduce my jump into the middle of this valley, okay? So, but they don't do that here, but so that's also another way how you can utilize these momentum terms. Okay. And then, yeah, so the biases, they initialize the zeros, and so on. Okay. This is kind of like how the network looks like. There's more up here, but and then as they mention in the paper, like if you use, so it's 1, 2, 3, 4, 5 convolutional layers, and 1, 2, and 3 max pooling layers, and each of these convolutional layers only has about 1% of the parameters. So like literally everything is in these layers here, right? So that's important, I think, that these upper layers are all the parameters that are there. So all this part here does. Can you like? Do you have an intuition what this part here basically does for them, so to say?
Extract.
Exactly, it's extracting features. It learns a representation that then is used in those upper layers to like identify. And so the cool thing about this is that you can actually, with that, realize that the filters have learned something so important or so successful that you can apply any function to that, or like you can learn to separate like these 1,000 classes. So that's not actually easy. Like to have 1,000 different classes, it's pretty difficult. And I don't know exactly all the, like obviously I don't know all the classes, but I know that there are a few in there. Like they're really hard. Like it's not just birds as a class, but it's like a typical bird. Like it's like bald eagle versus crane versus I don't know what. And so this is pretty tough task. Okay, so what does that in a sense then mean? So how could they have maybe gotten even better? Like, because this part here, all these convolutional layers, right? They don't really contribute to the classification. They only contribute to the feature extraction, to the representational learning. Or mostly, like. What could they have done to maybe even get better at that? And say, instead of 1,000, let's do 20,000 classes. Or keep it at 1,000 and you only use the training data. Well, so since this part here is responsible for the classification, this part is required 100% to be like supervised, right? So part here in the last 3 layers needs to have labels, and you can compute the loss based off of that. But these parts here don't necessarily require us to have labeled data. You can in fact actually think of like using this on a much larger data set and just basically try to deconvolve from here on and try to reconstruct the image here. So you could train these layers here also in an unsupervised fashion. So you could use much more data to maybe learn better representations that then help here. So in the paper they say that they opted to go fully 100% supervised and don't use any unsupervised data, but it could have been actually an improvement to like use 100 millions of other images to learn that. So I feel like it's kind of like a lesson that myself I have learned as well, like using these deep neural networks, where basically you're getting into the situation like, okay, I have big data, I have like 600-700 conversations or interviews with participants that suffer from depression and don't, and we want to do some machine learning on that. But 700 is actually not that much in the grand scheme of things, and you can always try to feel like if you have access to data that is very similar to what you're doing right now, but is not labeled, there's always seems to be like you can always try to find a way to actually incorporate that additional data into your machine learning problem, where you now have access to a lot more like data, and maybe your representations actually get better through that. So that's kind of like one of the things that we did in one of our papers. Quickly bring that up. So actually in this paper here, so we learned representation of emotional speech, which with deep convolutional generative adversarial networks, and so and a couple of you guys are using those DC GANs in their own projects. We used them as well, so we have the generator and discriminator here, and then at the end of kind of like the convolutional cascade of our discriminator, which looks exactly like this, right? And at the end of this basically right here, we take out whatever the activation of the neural networks are, and add one more layer like this, and learn 2 classifiers for activation and valence. And the cool thing is that this part here is trained unsupervised with a lot more data. So we have 2 data sets that we're using. Where is this? So we have one data set, the IMOCAP data set, that's 10 hours of data that we use for the supervised part, because that 10 hours of data have emotional labels like happy, sad, etc. But this corpus here, the AMI corpus, is a conversational corpus, like with like meetings in there, and it doesn't have labels, but we still used it, but because it's like 10 times as large as IMOCAP. And the cool thing is that just comparing the basic CNN versus the basic DCGAN, which the only difference between those two here is that this didn't have access to the unsupervised data that is not emotionally labeled, while this actually had access to that data. We get like a 5% boost for classification in those areas, and that's kind of cool, and like it kind of helps make the case that if you have access to unsupervised data and you have the time and the resources to use it, it actually sometimes makes sense to do that in your experiments. Okay, so that's another point here that is important. All right, so and then what happened? Why are we talking about this paper? What's the big deal? Anyone? Well, they're a lot better than everybody else. And it's not even close. Like it halves the error rate, and it's basically like crushing the competition at that point, and it was a very astonishing improvement. Can anybody tell me what the top 1 versus top 5, what that means?
I'm confused about it, but I think top 1 is like, it makes like 5 guesses on the images, right? So then I'm guessing top 1 is checking if the top guess matches the actual top guess.
Yeah.
So then I didn't really get what a top 5.
Top 5 basically just means is the correct guess in your top 5 guesses.
Oh, yeah.
So like if you have your softmax output, you basically the top 1 is like you only take the highest probability, and then like you compare that label with the actual label. So your prediction with the actual label, that's a top 1 error. So that's still pretty bad, right? So like 30% of the time, or more than 30% of the time, they're wrong. But then like top 5 is like you not take just the maximum, but the next 4 as well. So you have 5 guesses in total. So yeah, that's what that means. And you kind of can see that here as well. So yeah, so in this whatever agaric is, and then mushroom was only the second guess, and then grill whatever is the, I mean convertible. This is much more convertible than a grill. Madagascar cat, so that didn't show up here. Dalmatian and cherry. This is a good one, I think. Why is this happening?
Is it Dalmatian and
Yeah. So did you read about like what this data set is about, like how it was generated or created?
it used like mechanical churn?
Yeah. So like it might as well have been Dalmatian if a dog person rather than a cherry person has annotated this. So but yeah, it should have gotten cherry here, not grape and for child bull terrier. But what you also can see is kind of what's interesting here is to look at like these outputs here are basically the outputs of the softmax, and for example here it was super certain that it's going to be a Dalmatian, but then like every other guess was super uncertain, right? So there's not much support happening for all the others. So you're like, and sometimes you have less certainty, and the worst I guess is here, where you basically distribute a lot of the certainty across a lot more classes. So even the 5 top candidates here together only account up to maybe like half of the certainty or half the output. So that's also quite interesting to see that sometimes these networks are just very, very certain about some things, and sometimes they're very uncertain.
I have a question in regards to table 2, with the probabilities for top 1 and top 5. So why is top 5 lower? Like, does it have to do with, do they have to be in the precise order, or I guess I'm just trying to figure out what, like, what wouldn't the odds that like the first choice is within the top 5 somewhere?
These are error rates.
Oh, those are errors. Oh,
Yeah.
sorry.
So you're 60% correct and you're 82% correct here.
Okay.
I think that probably answers the question. Okay, so these are really cool networks, and they seem to perform quite well on classification. I just remembered a paper from last year that I thought was super interesting. Let me try to find that real quick. So, what the big story about that paper was, not sure if I can find it. So, oh no. Okay, so the main story there was just as a kind of like a caveat or something that is important to note. So if you take an image like, for example, the leopard here, and so there was a paper at ICLR 2016. They took a leopard image and put it through the convolutional neural network and tried to classify it. Works fine. So the classifier learns to classify this image pretty well and perfectly, and but they tried to basically look at like how the representation of that image looks like in their last layers. Okay, so they saw, okay, so this is kind of like it looks you know, like these it's basically like a collection of these filter responses, and it doesn't really look like an image anymore, but like it's kind of like a black and white kind of activation functions, etc. And then what they then did is they took another image and looked at what the convolutional neural network does for that image. So they would, for example, take the cherry image and see how the embedding or the convolutional outputs look like on that image. Okay, and then they tried to do the following. They basically learned a network that tries to change the leopard image very minimally, like changes like tiny bits of like the RGB values in the leopard image, to make the embedding very close to this image's representation. Okay, so it tries to change this image in a way so that in the end the representation of this image is very close to the representation of that image. Okay, and then they take the original leopard image and just add this change that they had to make to it, and then you show it to a human. And the human says, it's the same image. Like you can literally put those two pictures next to each other. You don't see a difference. There's no difference between those two images. Like you can't see it. And if you like see the difference image of those two images, it's very minimal, like a little salt and pepper noise kind of on that is added onto that image. Okay? But then if you take that altered image and give it to the previously trained neural network that knows that the original image is a leopard image, but you take that other image and you put that through the neural network, it thinks it's the cherry. These two images have nothing to do with each other, but the neural network's change in like the representation is so strong that it actually thinks it is receiving that image. So this is a kind of like a point of caution. Again, these convolutional neural networks do learn a lot of they overfit a lot again, and like they have this issue of like they are not robust to like these minimal changes, and these are very high frequency kind of changes, while a human doesn't do that. We don't perceive these high frequency changes, but the neural network is very susceptible to that. And so my idea to combat that I had when I saw that paper first time is like, you know, just smooth every image before you like put it into the neural network. And yes, you lose a lot of information, but you also remove a lot of like maybe sensor like bias from like a specific camera adds a little bit of a sensor bias, or these high frequency changes fall out, and you can actually probably still are able to recognize this. And that's why oftentimes you still want to do some pre-processing. You don't want to be just learning these high frequency differences between images that distinguish the two. And so again, like you want to make sure that the representations you learn are actually learning what you're interested in the image, rather than some additional like noise information that's present in the image. Okay.
Well, why does it still detect people of color as gorillas? I mean.
It does.
That's what I've had in the past. There was some saying people of color, they detect them as gorillas, and they're still trying to figure out why.
I think there was some, but yeah,
Has that been improved on?
I mean, it probably should be better by now. I don't know,
Okay.
like, but that is, I guess that was like the image search kind of thing.
Okay.
Yeah, I don't know, like, what happened there. And again, like, one issue could be that they're like that there might have been like faulty, I don't know, like issues in the training
Yes, I
or,
think, yes.
I don't know, it's, I think that is also like a really good point for, like we want to definitely, be more careful with rolling out, these solutions. Another one is the Microsoft chatbot thing that learned on Twitter and like became racist and
Oh, yes.
and
Oh, yeah.
within like hours.
Mhm.
There are just so many internet trolls that you never know. Like these are continuously learning
Yes.
networks and
Mhm.
like I think there need to be a lot more checks and balances before people roll out these networks, but I don't really know what happened there.
Okay.
But obviously, I mean, these networks always make mistakes, so.
Yeah, well, they're not us yet.
But,
They're not us yet.
no,
No,
they're not.
no,
Yeah, yeah,
in no way.
not even close, yeah.
In the sense that they're us
Yeah.
yet. Nowhere, and hopefully there won't be. So Elon Musk that.
If Elon Musk has his way, then they are gonna be. So, are there any other questions about like this paper that people have? Like maybe something that surprised you, something that confused you, or?
I just have a quick question. I know we talked about the GPU delegation earlier, but it didn't make the list. Should we add it to the list, or?
GPU delegation.
Yeah, I think the paper said because you ended up splitting the tasks
Ah.
between the GPUs, that's what also facilitated success, right? Or like that
Yeah.
extra speed.
So definitely the use of GPUs enables larger networks and faster training. What I'm actually intrigued by, and I think this is also what you're kind of getting at, is it is quite interesting that these two GPUs learned very different filters right away, and that kind of is also, I think is quite interesting in a sense because that probably only happened because either of them got different mini batches as like training data, or they just started at different location in like when you initialize the initial filter weights, and they learn completely different things.
So that wasn't on purpose at all?
I don't think so.
Okay, that's interesting.
I think they were just either lucky or it's so. And I mean, and then there's another thing that they did that we didn't add, I guess, which was this. Where is it? This local response normalization. It's just another kind of trick towards like controlling and managing the activation functions, the output of the neurons, and so this is so what this list in the end kind of looks like is they had to kind of okay, so it's value activation. That's not really new. Overlapping pooling is kind of a trick that they used. Dropout was relatively new back then. It's another trick that they used. Data augmentation, another trick. Some weight decays, adding some momentum term, using those different GPUs that learned different things, and then the local response normalization. So what this kind of shows is that there's a lot of like tinkering going into these neural networks, right? So you can get somewhere with a certain data set very quickly using just a general or standard like convolutional neural network, one layer is like connected output and so on. But really to improve over like the part that you get for free is a lot of tinkering, right? So you can get at a certain performance very quickly by just like, hey, let's do 4 layers of CNN and then like add another layer at the end. We do like max pooling in between, and we use all these kind of usual tricks. We do some dropout, fine, but like to get at this level, you have to do a lot of tinkering and one of the things that they say, like if you remove one layer, well, this would be 18%. That's not a big deal in contrast or in comparison to the other approaches. But to like squeeze the very last thing out of like your neural networks, that like requires a lot of like playing around and tinkering. And if you imagine that all of these networks, I mean right now like you can train this probably in a day, I think, but maybe back in back in 2010 or 2012, this might have taken like a week or two, and you didn't have access to. So we have now 12 GPUs, so we can run 12 models in parallel, basically, or we can run 3 very large models with like 48 gigabyte of GPU RAM, and so we can do a lot of these interesting things much quicker now, but the search space for these deep neural networks gets more and more and more complicated. So like you can add different things like you can why do you do like the max pooling here and here, why not here and here, and like this just like playing around and like trying to optimize what you're doing. Just like again as a word of caution, like you get like to like really optimize your networks, you have to still do a lot of engineering, and there's no theory of like why this is exactly the best network ever, right? So that's just another thing to remember, that a lot of times there's a lot of tinkering going on, and that can be quite frustrating. I know it from my students that they are not too happy sometimes that they train a model for like a week and then they're like, oh, it doesn't work, like, or it's not as good as the baselines. Like, yeah, keep on trying. That's all I can say.
Well, how about Google's GPUs? Will they be useful at all?
Yeah, I mean they're just gonna make everything another step faster, right? But I'm not sure like how fast we will get access to that. It just gives Google just yet another advantage over everybody else.
That and it's like really too.
Yeah.
They have the money.
They have the money, yeah. But I mean, they're doing good things as well.
Yeah, that's okay.
So still publishing a lot. You never know what they're not publishing, but.
Hey.
Who can say? Okay, other questions or concerns? Did anybody like think about questions with respect to like the finals or questions about the lecture in general?
Is the final comprehensive? Or
Yes.
okay.
I mean, over the entire class?
Yeah. Okay.
In regards to the papers that'll be on the final, is it just the ones that you posted on Blackboard or all of the ones on the syllabus?
I don't think you need to like know every intriguing detail of the papers.
But just like big ideas of the ones that you posted or all of the ones on the syllabus?
Most of the ones in Blackboard.
Okay.
I mean, I'm not gonna ask like, like how many layers did they use, or like what is the
It's
low
like- I don't know, just like the big takeaways, but I know like we
Yeah.
read some papers like earlier in the semester too, so I was gonna go over those, but then I think there were a few on the syllabus that we didn't discuss in class, so I just wanted
I mean, yeah, so there's always kind of like an issue, it's like, I'm not gonna recommend not to read them. But I'm also not like, not likely gonna ask questions specific to them. So, I think they're all pretty good papers and like, worthy to read, just to get like a better understanding of like the field itself and, pitfalls and useful things and, yeah. But yeah, so it's likely gonna be a class similar to like the quizzes and just like, you know, the same kind of structure, some open-ended questions and problem-oriented question. Even have like a bonus question where you can get extra points. It's like, it's a very simple bonus question, by the way.
Should we bring our calculator then too?
Yeah.
Okay.
How long is the final one?
I think it's 2 hours. Yeah, I'm always planning it to be like 1.5, but then, like there is a 2-hour slot. And everybody has time for 2 hours, and but usually you should be done by 1.5 hours. Yeah, and it's the typical type of questions that I have. It's like, obviously not gonna be the same as the quizzes, but, very similar. Like some general question, I don't know, what's overfitting? I think we had that already. Or, yeah, stuff like that. Plus, I mean, there's, you know, like, there might be, so one of the things that I asked you guys was like, write down like the base theorem kind of thing, and like, what are the 3 parts to it. I could ask a similar formula that you probably have seen around a lot. Like ask what those terms mean. I mean, it's not gonna be exactly this one, but like, if you saw something like this and it would be explained, it would be nice to know, okay, so this is the momentum term, this is the weight decay, and this is the, basically, partial derivative with respect to all the weights, of the loss function or the error function, and this is used to basically do the backpropagation, that's why we have a minus here, and so on. So, if you see a formula like that, it'd be good to know like what the parts of the formula are, and this is the learning rate here and stuff like that. That could be in the final. I'm not sure. What else should you know? And then, I mean, yeah, so in the slides, when you go through the slides and you see like words in bold or in italics or something like that, that might be important to remember. Things that we talked about once briefly, and I'm like, you know, this is for your reference, but don't think about it more, then you know that this is not going to be part of the exam. But yeah, so sometimes if I mention like something in bold, I guess like that would be important.
Are equations in red boxes very,
Equations in red boxes, I don't remember any of those.
I can't remember off the top of my head, but I know like every now and then there would be like a big red box around an equation, but it was a bit more complicated than like base theorem. I think I'll have to find an example.
Oh, I remember what it is. That is the regression function.
I think there was,
Or
there were
regression.
a couple of them. I can't remember what one was. I'll find them and send them to you. Oh, they're all in the
Like in the kernel machine.
Yeah, probably.
I mean, something like that, for example.
Equations.
No.
Not like that.
So like here, this is a nice function.
Yeah. That's the
Like you can talk a lot about this function. There's a lot happening here. But I think I know what you mean. Yeah. So that in the kernel, the Lagrange thing.
Oh yeah, here we go. Yeah, there's a bunch in there.
No.
No.
No, don't worry about that.
Okay, that's really good.
Oh yeah, no. Oh god.
Language multipliers.
But then you know,
Oh,
Yeah.
no.
oh yes, this one here as well, right?
Shows you this.
But this one's not that
Yeah.
hard.
Yeah.
But in general, I mean, like this just gives you, it's a linear equation system. That's how you get that, and it has a analytical solution rather than like a stochastic or like a gradient descent solution. But this stuff is also cool. So like bias variance trade-off and stuff like that. What else? Yeah, and then we talked about, we talked about maximum likelihood versus expectation maximization. I think that would be interesting. In general, like, I'm just on that lecture, like 11, where we have like hidden Markov models. I think hidden Markov models are interesting. And then all the way back, I guess we talked about like what is a hypothesis space and stuff like that. And the Vapnik-Cherenkis dimension, whatever that means. I think there's a lot of like so hard questions that you can imagine, and then some problems like we had. Did we do naive Bayes already in that quiz? Yeah, I think so. And then we did a graphical model. Does everybody know how to draw perceptrons and solve Boolean functions with perceptrons? You can look into that. That's an option. That doesn't mean that that's part of it.
Yeah, like if mapping a perceptron, like to solve some Boolean.
Or explain what a kernel is, what kernel methods are good for, and stuff like that.
The AI part.
Yeah.
Yeah, it's like similar in that way.
Are there any other questions or? I still haven't heard.
Is it the 8th at 8 a.m.?
Oh, yeah, wait. They have this already often, don't they? Final exam schedule.
Schedule for
So it's May 3rd to 10, and then, so we are 10 or 10:30, Monday, Wednesday, Friday, so our exam's gonna be on Monday, May 8th at 8 a.m. Jesus Christ.
we have our NLP.
Because we have.
One month,
just
yeah, I
until
should find
9 o'clock
things.
to make them one Zoom.
Oh.
And we have 5 of them from the same course.
You have an NLP?
Yeah.
Yeah,
and
yeah,
the
On the
same-
same day, yes.
Yeah.
And we have 5 of us from the same course.
When is that?
It's like,
That's the evening at 4.
most of us
When
get
is
to.
it's when is the NLP exam?
I think it's on Monday. I
On
can't
Monday.
remember.
4:30.
It's right.
4:30 for the final.
Oh, really?
Oh my.
Where can we find those?
Oh,
Final
4:30.
exam?
He's
Final
putting
content,
Yeah.
It's like on the classes at USC.edu.
Yeah.
Yeah, it's a.
Is that a
It's a
Monday?
Somebody give you a new code.
Oh, God.
Oh, this is not the other class.
Yeah, it's Monday.
Natural.
Yeah.
I can ask Liesel if she's able to change that. But I don't.
I doubt it. I don't think maybe the batch ones should have 2 exams on Sunday.
No, yeah.
So you certainly, so the NLP is definitely on the May 8th. And from 4:30. I do not envy you. Okay. I'll ask if we can move it, and since we're small class, maybe find a way. But I can't promise. Okay. But I guess they're being fair because like the classes that start at 8 on Monday, Wednesday, Friday get the 11 a.m. and the class that starts at 10 gets the 8 a.m. It's like we haven't been like tortured to wake up that early through the entire semester, but like one day.
Wouldn't it be like counterintuitive? Because they always say you're supposed to like study how you test, so then like if you wake up early and you're used to experiencing that subject early, shouldn't you have to test that early?
That's fine. Yeah, I'll investigate that. I'll let you know. But I don't think there's a lot to fear about this exam. So. Okay.
So I have this saying which says, still have many order of magnitudes to go in order to match the interferon temporal pathway of the human visual system.
That's very true. Alright, so I guess we'll have one more class, so if you have questions with respect to the exam or like the content or your course project, I think everybody should like prepare or think about something there. And I'll do the I'll give you the feedback on the quiz by then too. And what else? Yeah, if you have any like problems or questions about the course project, like definitely present them or bring the questions. And if you have any exciting results, I would be happy to see some as well. So the final submission will be at the end of that week with the exams. As I think I've already sent an email about that. Okay. Right.
So doing Kaggle competitions, is that a good way to get into this, moving along, doing competitions?
Yeah, I mean, those competitions are nice to do, I think.
Okay.
But I think people are kind of trying to break it as well.
Okay.
Oftentimes.